30 meters below a cathedral. Servers hum quietly. Worshippers above never feel the heat rising beneath their feet. Nearby granite caverns are ready to hide nearly 1 million people within hours. Helsinki built a city that can survive a war. Welcome back to the channel. What you're about to see is one of the most extensive underground urban systems ever attempted, the underground city of Helsinki, an entire layer of the Finnish capital carved into solid granite bedrock. This is not just a basement, it is not just a few tunnels strung between buildings. This is a self-sufficient second city, complete with churches, swimming halls, data centers, water treatment plants, heating plants, parking caverns, and shopping streets, all running beneath the surface that most visitors never think to look under. And every single part of it was planned, mapped, and legally protected before a single drill ever touched the rock. To get there, the city had to overcome almost everything working against it. Bedrock so hard it has to be blasted ton by ton just to make room for a single corridor. Winters that drop to 20, even 30 degrees below zero. Barely 6 hours of daylight in the depths of December. A long, sensitive border with a much larger neighbor to the east. A fact that shaped Finnish civil defense thinking for generations. A population that, by law, needs a shelter built into almost every large new building. Groundwater that seeps into freshly blasted rock the moment it is opened. Bedrock quality that can shift every few meters, forcing engineers to reassess constantly. The need to keep heating costs low through 9 months of cold. The need to leave surface land free for parks, for housing, for daylight. Decades of separate agencies, separate contractors, and separate decades of work that all had to be mapped onto one coherent plan, so that one new tunnel never collided with an old one and one new cavern never undercut a building. And they decided, in the face of all of that, to build a second city underneath their own. Before we continue, make sure to subscribe, because this channel covers the engineering stories most people never hear about. Stay with us until the end, because by the time this video is over, you will understand why a children's playground in Helsinki can be turned into a bomb shelter in 72 hours. At first, there was only granite. No tunnels, no churches, no swimming pools, just bedrock, hard, ancient, sitting close to the surface, utterly indifferent to the small, low-rise city, slowly spreading across the top of it. The rock had been there for hundreds of millions of years. It did not know about zoning laws, or metro timetables, or winter heating bills. It simply sat there, dense and indifferent, and waited to see what the city would do next. If Helsinki had simply expanded outward, it would have consumed the parks, the coastline, and the green space that make the city livable in the first place. Helsinki is a city built on a peninsula, hemmed in by water on 3 sides. There is only so much surface area, and once it is gone, it does not come back. If it had built upward instead, with towers and high-rises stacked against the sky, it would have lost the low, light-filled skyline that defines it. And during a 6-hour winter day, extra height does nothing to help anyone escape the cold or the dark. A tower flat on the 30th floor of a Helsinki skyscraper in February is not a solution. It is just a different kind of problem. So the solution was not a single basement, and it was not a single bunker hidden under one important building. It was a master plan, an official citywide map of everything that could exist beneath the streets, coordinated so that decades of separate projects could fit together like the chambers of one enormous deliberate structure. The City Council approved it as a legally binding document on the 8th of December 2010, though the process of mapping and cataloging underground space had been underway since the 1980s. By the time it was formally codified, Helsinki already had more than 400 separate underground premises. The plan did not invent the underground city. It finally gave it a legal spine. It started with survey and research, because no one blasts into solid rock without knowing exactly what is underneath it. It was anything but. Geologists fanned out across the city, mapping the bedrock across every district, identifying the zones close enough to the surface to be worth excavating, and strong enough to hold a structure once the rock was removed. Engineers drilled boreholes to test rock quality meter by meter, pulling up cores of granite and reading them the way a doctor reads an X-ray, looking for fractures, for water channels, for seams where two different rock formations met at an angle that could cause problems decades later. Hydrologists tracked where groundwater moved through the stone because water in granite does not flow like a river. It seeps, it collects, it finds every new crack a blast creates. Structural engineers calculated how close a new cavern could come to a building's foundation without weakening, running calculations for structures that had never been designed with a cavern in mind when they were built. Rescue and civil defense planners worked through regulation by regulation, working out how every large new structure could double as a shelter without ruining its everyday use. Acoustic engineers, fire safety designers, ventilation specialists, traffic planners, and urban coordinators all had to look at the same rock and agree on what could go where and what could never go there at all. Every survey mattered. A single missed fracture line in the granite could mean a flooded cavern decades later. A missed structural calculation could mean a building shifting above a space it was never designed to float over. Then came the work of turning that survey into the legally binding plan itself, so that every future project would have to check itself against the same master map before a single drill ever touched the rock. Nothing could be built in the dark literally or figuratively anymore. Then came the ground preparation, and this is where the real violence of the project begins. Workers drilled patterns of holes into the granite and packed them with carefully calculated explosive charges designed to break the rock loose without shaking apart whatever sat above it. Blasting in open countryside is a matter of power and efficiency. Blasting beneath a living city is a matter of millimeters and milliseconds. Each charge had to be sized precisely so that the energy traveled downward and outward into the rock rather than upward into the foundations of a hospital or a school or an apartment block. Each blast had to be timed so that its shockwave did not compound with the shockwave of the next charge along the tunnel. The whole sequence had to be modeled before a single detonator was triggered and then monitored in real time as it happened. Engineers reinforced weak sections of rock with steel bolts driven deep into the stone, sometimes meters deep, anchoring unstable layers before they could shift. They sprayed shotcrete across ceilings that needed extra strength, building a composite surface of rock and concrete that was stronger than either alone. Pumps ran constantly from the first day of excavation, pulling groundwater out of newly opened chambers before it could pool and freeze. Or worse, start to dissolve the fine particles between rock layers. Drainage channels were cut into the floors of active tunnels to keep water moving away from the workface. Ventilation fans pushed blast dust and diesel exhaust out of tunnels that, at this stage, had no natural airflow at all. Mesh netting was bolted across ceilings prone to loose rockfall. Drill rigs, explosive charges, rock bolts, shotcrete applicators, ventilation fans, water pumps, drainage piping, rockfall mesh, surveying lasers, fiber optic monitoring cables, ground-penetrating radar units, and dump trucks hauling away broken stone became the daily rhythm of the work. At the Viikinmäki site alone, crews eventually excavated approximately 1.2 million cubic meters of rock. First around 1 million cubic meters in the late 1980s and early 1990s. Then another 200,000 cubic meters a decade later when the plant needed to grow. That is enough broken granite to fill roughly 500 Olympic swimming pools. And Viikinmäki was only one site among dozens. This was not digging a hole. This was carving rooms, corridors, and entire halls out of a mountain that did not want to give them up, one controlled detonation at a time. Then came the primary structures, the places where raw excavation finally became architecture. Imagine standing at street level in TL in the late 1960s, looking at nothing more than a rocky outcrop rising out of a city square, unremarkable to anyone walking past. Architects Timo and Tuomo Suomalainen had won a competition to design a church on that exact spot. And their plan was almost too radical for the jury. Leave the rock walls exposed. Leave them rough and unworked and blasted. Looking, instead of hiding them behind smooth concrete panels or tiled surfaces. This was a provocation in 1960s architecture. A church was supposed to elevate. A church was supposed to polish away the rawness of the world, not celebrate it. When acoustic specialists ran their tests and confirmed that bare granite would actually improve the church's sound, that sound would bounce off those rough walls with a richness that a smooth surface could never produce. Construction began in February 1968. Workers blasted the interior space directly out of the rock, shaped it into an elliptical hall, and topped it with a copper dome ringed by a continuous skylight that lets natural daylight pour straight down the granite walls throughout the day. The church, Temppeliaukio, was consecrated in September 1969. Today, it draws approximately 500,000 visitors a year, making it one of the most visited sites in the entire country. And underneath it, deeper still, sits a Cold War era shelter now used as parking. The church needed the rock. The rock needed careful blasting. The blasting needed acoustic testing before anyone trusted it. Every link in that chain was deliberate, and every link held. Then came Itäkeskus, on the other side of the city, where engineers were not building a single sacred room, but an entire recreational complex on 2 underground levels. Workers carved out a cavern large enough for a 50-meter competition pool, divisible into 2 25-meter pools, for simultaneous use, alongside a children's pool, a cold water plunge pool, water slides, diving boards, several saunas, a steam bath, a gym. The logistics of supplying a space like this underground are not trivial. Every pipe carrying hot water to a shower, every cable powering a pool filtration pump, every drainage line carrying used water back to the surface had to be planned into the excavation before the rock was removed. Because retrofitting underground infrastructure is not like retrofitting a building above ground. You cannot easily open a wall and reroute a pipe when that wall is solid granite. The hall opened in 1993, and today it can hold around 1,000 visitors at a time. It is a public space that feels genuinely generous, wide, well-lit, warm in winter, and cooler than the surface in summer. But because of the same shelter laws that shape the church and almost every other large structure in the city, that same swimming hall can be converted into an emergency shelter for approximately 3,800 people. Without that legal requirement, the space might never have been built to this standard. With it, the city gained both a public swimming pool and a fortress, occupying exactly the same rock, serving 2 entirely different purposes. Then came Viikinmäki, where the challenge was not recreation or worship, but survival on an industrial scale, treating the wet whir of a population that would eventually reach roughly 800,000 to 890,000 people. This is not a glamorous engineering problem. It is in some ways the most important one. Engineers excavated chambers for mechanical screening equipment that remove solid debris, biological treatment tanks where microorganisms break down organic matter, chemical treatment systems that remove phosphorus and other nutrients before water reaches the sea, sludge digestion units that croppers the solid material removed from Weechen and converted into biogas the solidarment. The plant was commissioned in 1994 and remains the largest wastewater treatment plant in Finland and the Nordic countries. This was not a single tank buried under a field. This was an industrial city in miniature, built entirely inside a mountain, running continuously, invisibly, around the clock, 365 days a year, for 3 decades and counting. Then came Cathedral, where engineers asked a different kind of question entirely: what if the heat the city was already generating as a byproduct of other processes could be captured and reused instead of being thrown away? In a cavern blasted beneath Cathedral Park, a park that residents walk through, sit in, and use without knowing what runs beneath it, a heat pump plant began operating in 2006. The plant draws thermal energy out of purified wastewater and converts it into district heating in the winter, warming homes and offices across the city through the same pipe network that carries heat from other sources. In the summer, the exact same equipment runs in reverse, drawing heat out of buildings and depositing it into that same wastewater stream, providing district cooling. It is described as the world's largest plant of its kind. The symmetry of it mad. The same machine, the same pipes, the same physics, delivering warmth in February and coolness in July. The plant needs purified water, The Wantre needs the Viikinmäki treatment process upstream. The treatment process needs the granite cavern that holds it all. Every link in that chain had to exist before any of them could function. Then came the data centers. One of them sits roughly 30 meters below a cathedral. It is cooled not by banks of air conditioning fans exhausting heat into the city air above, but by seawater drawn from the harbor, circulated through heat exchangers. The waste heat that would otherwise be lost is instead captured and piped into the district heating network, warming apartments and offices kilometers away from the surface. Nothing gives it away. There is no cooling tower, no rooftop machinery, no visible exhaust. Just the quiet of a city going about its day, unaware that a data center is humming in the dark beneath one of its oldest buildings. Then came the secondary structures, the connective tissue threading everything together. Metro tunnels linking stations beneath the city center, beginning with the systematic excavation into bedrock that started in the 1960s. Pedestrian passages connecting metro platforms directly to shopping centers, so that a traveler in Helsinki can walk from a train to a store to an underground parking garage. Parking caverns, roughly 30 of them across the city, carved into the rock instead of laid across surface land that is too scarce and too valuable to surrender to cars. A network of technical tunnels carrying electricity, telecommunications cables, water supply lines, and sewage pipes beneath the streets, all mapped against the same underground master plan so that a new data cable never accidentally cours through an old water main. A district heating pipe network stretching nearly 1,600 kilometers beneath the streets, delivering hot water from plants like Cathedral into homes across the city, keeping buildings warm without anyone needing to burn fuel locally. From above, none of this is visible, but below an entire second circulatory system keeps the city warm, lit, connected, and clean, and it has been doing so quietly and without interruption for decades. Then came the interior finishing work, the layer of effort that transforms blasted rock into a place that human beings actually want to be. In, lighting systems designed to compensate for the absence of windows and the shortness of winter days, calibrated carefully to avoid the institutional coldness of underground fluorescent light while still providing enough brightness for safety and usability. Signage and wayfinding systems guiding people through tunnels and corridors that without them would feel genuinely disorienting. Color, texture, and material choices that make a carved granite ceiling feel like a design feature rather than a limitation. Blast doors built directly into the walls of dual-use facilities, folded flush with the surface during ordinary use, but capable of sealing a space within hours when needed, their hinges and seals maintained and tested regularly. Air filtration systems installed alongside those doors, designed to keep a sealed shelter breathable for days at a time without any connection to the outside air. Heating systems calibrated to the unusual thermal properties of solid rock, which holds a stable temperature year-round, far better than any above-ground wall. Neither as cold in winter as the surface above it. This was not decoration. This was the layer of work that decided whether a cavern felt like a tomb or like a public swimming pool. And in Helsinki, they chose the swimming pool. Then came testing, because a shelter that has never been tested is not really a shelter at all. It is a room with a blast door on it, which is a different thing entirely. Current planning guidance requires that Helsinki's dual use spaces, the same pools, gyms, playgrounds, and parking halls that serve the public every day, be capable of converting into full civil defense shelters within 72 hours. 72 hours is not very long. It means that blast doors must be operable by whoever is on duty that day, not just by a specialist called in from across the city. It means that air filtration systems must start reliably after years of sitting unused. It means that water and food provisions must be staged and rotated. It means that sleeping arrangements for thousands of people must be deployable from storage in a hall that was hours earlier, full of recreational swimmers. That is an engineering problem and a logistics problem and a training problem all at once, and it requires ongoing rehearsal. Geotechnical monitoring continued long after construction finished, with boreholes and sensor tracking, looking for any sign that a fracture was widening, that a water channel was shifting. Then came final inspection. And with it, something unusual for a project of this scale. The underground master plan itself is a living legal document, reviewed and updated as the city grows denser and finds new uses for the rock beneath it. Helsinki is not finished. Every new structure over a certain size still has to satisfy the same rescue, shelter requirements that shape the church. New underground projects still have to check themselves against the master map before a drill touches the rock. Nothing about this project ever really finished. It simply kept being inspected, kept being renewed, and kept growing, adding new chambers to a system that had been adding them since the 1960s and shows no sign of stopping. Most residents only see the entrance to a metro station, or the door of a swimming hall, or the quiet square above a church cut into a rocky outcrop. They have walked past 100 times. They do not see the boreholes that mapped every layer of rock before a single charge was ever set. They do not see the rock bolts holding up ceilings that were once dangerously unstable, sitting invisible in the granite above them as they swim their morning laps. They do not see the pumps running around the clock to keep groundwater from flooding chambers that took years to carve. They do not see the blast doors folded flush into the walls of a children's gym, waiting for an emergency nobody wants to imagine but everybody has quietly prepared for. They do not see the pipes carrying server heat from 30 meters below a cathedral into the radiators of apartments kilometers away. They do not see the 8-kilometer tunnel carrying treated water ration silently beneath the seabed to a release point 20 meters down. They do not see the 1.2 million cubic meters of granite that had to be removed, hauled away, and disposed of before any of this could exist. From above, Helsinki looks like a calm, low-rise Nordic capital, full of parks and harbor views and a skyline that never quite breaks into towers. But below, it is something closer to an organism, a living system with a circulatory network of heat, water, electricity, and data running through rock that was never supposed to hold a city at all, and has been holding one for 60 years. Helsinki did not conquer its bedrock, it listened to it, mapped it, and built around its weaknesses instead of against them. It did not defeat its winters, it went underneath them, into a layer of the earth that barely notices what season it is, where the temperature stays stable and the wind never reaches. It did not abandon its small, quiet skyline for one full of towers. It built a second skyline, inverted in the dark, pointing downward into the granite instead of upward into the sky, where almost no one would ever think to look for it until a video like this one pointed a camera straight down. If you enjoyed this, subscribe to the channel, because there is a whole world of engineering hidden beneath the cities you think you already know. Thank you for watching.